All right, welcome back, everybody. As our last speaker of today, we have Juan Carrasquilla from Vector Institute. He has Juan and his former advisor, Roger Malco, have written a really pioneering paper where they proposed using neural networks and machine learning models for phase detection as opposed to face detection, and really set the community into a path of this adventurous path of trying to use these tools to gain better understanding of many quantum states. I'm very happy to have Juan as our speaker today. And without more, I will have Juan take over.
Thank you so much for the kind introduction and for the invitation. It's a pleasure to be here. It's been fun to participate. So I'm going to tell you about many-body physics with a particular set of models called autoregressive models. So basically, I'm going to start introducing the problem of high dimensionality in quantum mechanics and why it is important and what we use or what we do typically to overcome it, right? Like make progress in this problem. So the first thing is to tell you that the generic specification of a quantum state requires resources that are exponentially in the size of the system, like say the degrees of freedom n. For instance, for a spin 1/2 system, the quantum state is a vector with 2 to the n components, so it's very fast growth. It's so bad that today's best supercomputers can solve the wave equation exactly for a system of up to 45 spins already, using some of the knowledge we have about the systems, such as symmetries and conserved quantities and so on. So, but the problem is we have a lot of problems, right, that are technologically relevant in chemistry, in condensed matter and quantum computer that are much larger than 45 spins. And so we have to learn how to handle this complexity, right? Like, so we have to, what we say, we exploit the structure of the problem to make progress, right? And so it's because typically we have this exponentially big vectors, but the amount of information is typically smaller than this maximum capacity, right? And so we can exploit that structure. And so this is what we do, for instance, what we do when we use techniques such as quantum Monte Carlo, where instead of using all this 2 to the n configurations to compute expectation values and so on, we do a stochastic exploration of the most important regions of this gigantic space. And these regions typically are small, and so you can sample them and make progress, right? Compute correlation functions for systems that we care about in condensed matter physics and many-body physics. There's also a different approach. It's called tensor networks, which are, if you want, parametrizations of quantum states, which are, and what we exploit is the fact that quantum states realized in nature have little entanglement, right? Like so, and then we propose this ansatz, which are based on this idea that low entangled states are easy to represent using this tensor networks. And both techniques, quantum Monte Carlo and tensor networks, have led to profound implications to our understanding of condensed matter systems. And then what we bring in machine learning to the game, and the idea is that the machine learning community deals with equally highly complex problems, but nevertheless that are very structured as well, because they arise, many of these problems in machine learning arise from trying to, say, classify or understand data sets arising from like nature, right? Like pictures of cats and so on, right? And so the insight, or what I want to propose, is that both quantum physics and machine learning have a lot of structure and even some shared structure and symmetry that we can exploit, and that this is what allows us to use all these techniques to make progress without even doing a lot of changes to the architectures and so on. So there are commonalities, right? Like structure and symmetry. So what are these commonalities, and are they important, right? Like beyond mere like high dimensional resemblance, right? So that's the question. And so like the first one is high dimensionality that I mentioned. So in quantum mechanics, quantum state is 2D, like 2 to the n dimensional vector. And so with n of around 45 particles, we have state space about 3.5, 10 to 13 dimensions, so that's a lot. But then I wanted to point out that, for instance, one example in machine learning is language translation, and then people construct models, right? Like, and these models live in very high dimensional spaces that, for instance, this is from a paper called Attention is All You Need, where like the size of the state space is defined by the, like, I don't know, the maximum length of a sentence, and then the local, if you want, like the equivalent of the local Hilbert space is the vocabulary size, right? Like, so for instance, if you are going to read a typical article in the BBC news, it's about 8,000 words that you want to understand, and then say for a paragraph with 100 words, then you have a 8,000 to 100, which is very, very big. Okay, so this is a very large state space. So that's the first commonality, high dimensionality between the problems that we tackle in quantum physics and in machine learning. But then there's more, right? Like there's there's correlation functions that are very similar in structure, right? Like, so for instance, correlation functions in natural language and natural images typically are power law correlated, right? Like music is also power law, and flocks of animals display also this power law decay correlations that are very similar, even identical to a classical or quantum system at the critical point. And so this has been studied, for instance, there's this paper where they study Stalin flocks, where they find that they behave as a critical system. This is for natural images. Behave similarly to the Ising model, where t equals 1. This is really close to kind of like the phase transition, if you want, in the image space, and more, right? Like, so, and then in addition to it, there's translational, rotational, reflectional, and other symmetries that are very rich, and that simultaneously improve the computational complexity of machine learning algorithms, but at the same time enrich our understanding of many body physics and quantum mechanics in general. And so that, I think these are all the reasons I believe are important, and kind of like a motivation for why maybe using machine learning techniques is a good idea as like for a tool to tackle problems in many body physics. Okay. But I wanted to focus on autoregressive models. And so what are these? So the term autoregressive originates from the time series models. So where like the observations from previous time steps are used to predict the value of current time step, right? Like, but I want to understand this, or I want to show you this in the context of probability. And so for a probability distribution over variables sigma 1 through sigma n, you can always decompose this through this probability chain rule, where you write down this probability distribution as probability of sigma 1 times probability of sigma 2 conditional on sigma 1, and so on. And you see that this is the autoregressive nature in there, where like previous variables that you have observed, if you think of this sigma 1, sigma 2 through sigma n as a time series of spin variables or variables, and then you use sigma 1 and sigma 2, the previous time steps you observed, to predict the probability of sigma 3, and so on. So in general, like, you can specify any probability distribution in a tabular form, but this requires specifying all these conditionals, and so this requires exponential resources. But what people in machine learning and in statistics realize is that you can alleviate this exponential issue, or this exponential complexity of specifying this gigantic distributions by parameterizing just the conditionals, right? Like, so if you instead of specifying every single value of the probability distribution, you just simply parameterize this conditional or each conditional, then you alleviate the exponential complexity, as long as the number of parameters you put in your model is small, right? Like, it doesn't scale exponentially. And so these models are very interesting, and they have a lot of advantages in my opinion. So they can be, for instance, they can be exampled exactly easily. You can compute the probability of any configuration sigma easily, because they usually become normalized. So you don't have to deal with a partition function of the model and so on. They can be defined in any spatial dimension. they're easy to encode mean field theories, for instance, Fitzwiller mean field theories, or any of like simple mean field theory we can think of. We can impose symmetry and other inductive biases that are useful for the application to the specific problems that we care about. And these problems remain true even for models of the wave function, right? Like, so you can generalize this probabilistic models to a quantum state, and these properties remain, right? And so I think they're very interesting. So let me give you one example of a canonical, if you want, example of an autoregressive model, the so-called recurrent neural network. And so the key building block of a recurrent neural network is the recurrent cell that I highlight here in green, this RNN block. And what this RNN cell is just a nonlinear function. So, and this function takes input the so-called memory state or internal state of the RNN at step n-1 and the spin configuration sigma at n-1. And it does so through these parameters in the model, which are the matrices W and the vector B. And then it outputs this vector, right? It's the new memory or internal state vector. And so you see there's a recurrence relation where the the nth vector depends on the n-1. And so because of this recurrent behavior and the dependency that is generated by calling this function multiple times, this internal state vector can be used to parameterize this conditional, right? Like, because this vector is going to depend on the right set of spin variables. And they're going to be correlated through the fact that you have this vector that, if you want, encodes the correlation between the variables, right? Like, and so what you do is you take this this hidden vector h, and then you use a so-called softmax to produce a normalized condition, right? Like, so you get this conditional distribution with the right, if you want, chain rule structure, right? The other thing that is important that I mentioned already is that this model is a structure so that you can sample it efficiently by just simply sampling each of the conditionals and feeding the samples that you get out of the model. And then the last thing I wanted to mention about this, which is very nice, is that they're all universal function approximators, which means that in principle there's hope that they can say compute functions that are complex and that are rich, that are helpful for problems that we care about in many-body physics. But
there's
the
a
list
question.
is, oh, yeah, go ahead.
Question is, what if we have quasi-probability instead of positive definite probabilities?
You can make it into a complex quasi-probability, and we've explored some of this, I think, in one example. So not necessarily negative, but still a quasi-probability, okay? But in principle, they can be generalized to quasi-probabilities, to complex wave functions, and so on. So, yes. So let me go ahead. So there are many more models that are very powerful and interesting. There are transformers, neural autoregressive density estimators, many more, right? They're all very, very interesting and very powerful. And so today, so what I want to tell you is it's about a probabilistic formulation of the quantum state, which is, if you want, going into the direction of like taking quantum mechanics and making it look like machine learning, as opposed to like taking machine learning models and making them look like quantum states, which people do. But then I'm going to give you several examples. So one of them is learning quantum states under dynamics. Then I'm going to introduce recurrent neural network wave functions quickly and show how powerful they are. And then I'm going to finalize with variational neural annealing, which is the last thing I want to tell you about. And so a probabilistic simulation of quantum mechanics. So this is motivated by Feynman and this simulating physics with computers, one of the papers that motivated the field of quantum information. And there's section 5 that is very interesting. So he asks, can quantum systems be probabilistically simulated by a classical computer? And then the answer is no, because when you try to express the quantum state or the dynamics, you start seeing positive and negative signs around. And this is, if you want, the presence of those signs is tied to the fundamental like speed up of the promise of the quantum computers, right? Like, so that's the conclusion. Even in 1981, this is very difficult to do if you want to do it exactly. But then we asked the question: can we do it approximately if we have machine learning models, right? Like, can we simulate quantum physics with probability at least approximately, right? That's the question. And so first we came up with a probabilistic representation of quantum mechanics. So typically in quantum physics, we represent the quantum state through a density matrix, which describes the statistical ensemble of the system, right? Like, so for one qubit is the Bloch sphere, or it's a vector in here in the Bloch sphere. But there are alternative representations, and the question is, are they useful, right? Like, so one of them is this, the one that I'm going to introduce is a probability representation of the quantum state. So how to do it, right? That's the question. So we use measurement operators, right? Like, so we use positive operator value measures, POVMs, and the idea is that there's a relation between quantum theory and experiment, the so-called Born rule that connects the quantum theory, the density matrix, the state, the measurement that you use to on the system, and the probability of observing outcome A, right? Like whatever it is that you're measuring, you get outcome A. So the probability of finding A is given by this Born rule. It's a fundamental connection in quantum theory. And this measurement operators, POVMs, there's a list of them, and they're positive semi-definite, and they add up to the identity, okay? And now, in general, you wouldn't be able to represent the full quantum state as a probability just by simply measuring a couple of POVMs or measurement operators, but there are so-called informationally complete measurements where the statistics of those operators contain all the information about the quantum state. And the analogy or the geometric cartoon is you have a quantum state, it's a very high dimensional object, but if you measure it from different angles, then eventually the statistics of the measurements will will specify the quantum state. And so in those cases, then the relation between the density matrix and this probability distribution can be inverted. And so this is the inverse. So, and I use a lot of this graphical notation of introducing tensor networks, where like here is the Born rule, the blue is the density matrix, these are the operators that you measure, and this is the probability distribution. So this relation can be inverted, and you can represent the quantum state as in terms of a probability distribution with some tensors attached to it. And then everything in quantum theory follows from there, right? Like you can study unitary evolution, the Schrödinger equation, Limblad equation, and so on. So for instance, here you have this von Neumann equation for the dynamics of the quantum state rho and the Hamiltonian dynamics. And then if you map that into the probability language, then you get a master equation for the quantum state. Okay, so that's what I'm using here. I'm using this probability representation of the quantum state. And the insight we had was, okay, we can do that. We can use models introducing machine learning to parameterize this PA, and then by plugging that model into that expression, then we get a model for the quantum state, okay, composed out of machine learning model and as few, like a simple tensors attached to it, okay? So let me give you an example of an application of that. And the example is quantum state tomography. The idea is that you want to prepare a quantum state and you want to kind of like see if you can learn this state or approximately learn the state. And so you prepare the state, you apply these measurements, right, that I was describing, and then you repeat and collect the statistics of this measurement. And then you infer a reconstruction of the state in terms of this probabilistic model. So we introduced that idea in this paper. And then these are examples of what we've done. So these are learning ground states of local Hamiltonians, and A and B is the transitional Ising model in 1D with 50 spins. And what we recover is this green dots that are, if you want, are learned states with comparison with the DMRG results that we use to produce this data sets, if you want, these measurements. And so that's nice. And these are synthetic states of the Heisenberg model in 2D on the triangular lattice. And this is the synthetic state, the correlation functions, and these are the reconstruction of the states that we use using this probability distributions. Okay, so we were pretty happy about that. And then we went ahead with in collaboration with Una, the chair, and Peter Cha, who is attending. We did a little experimental demonstration where we learned a GA set state prepared with 3 qubits, which is very interesting. It's already been already on the archive, but just to mention that we can use these tools to play with the experiments, right? Then we took, okay, so that's kind of like you have data and you want to reconstruct the state, but can we use this representation to simulate quantum dynamics, right? And so the first example we looked at was, can we simulate quantum circuits? So we did that, right? Like, so a quantum circuit is simply a unitary operation acting on an initial state rho. And so you get this unitary rotation of the density matrix, and then you measure, and that's how roughly, very like a few words, what quantum circuits do on a quantum state, or it's a big unitary that you construct out of like a tiny unitary gates. And it turns out you can map all the language of the quantum circuits and so on into the probability representation, right? Like that's the idea. So we use Born rule, and then we map this expression here, which is how you evolve unitary matrices and how you evolve probability distributions, right? Like, so you go from an initial distribution P into rotated distribution PU through an object that I call, or that some people call, a somewhat stochastic matrix. And this matrix, of course, depends on the unitary that you are applying, okay? And so this evolution is almost classical, right? Like, because it's like, if you could interpret A prime, A double prime as a conditional distribution, then this is basically classical. You could simulate it exactly with Monte Carlo, but these gates, these probabilistic gates come, I mean, they're almost like a stochastic matrix in that if you sum over the columns, they sum add up to 1, but they can be positive and negative, right? So they're not easy to simulate with Monte Carlo. So what can we do? So well, we will approximate this distribution PU with a model, with a probabilistic model. So we take an initial distribution, we want to multiply it by a somewhat stochastic matrix, and this results in an evolved distribution PU that we will approximate, okay? And so the idea is, this is difficult to do in general because these are very high dimensional. So what we do is we introduce a model P theta, a probabilistic model of the quantum state. And then what we found out is that it is easy to compute the KL divergence between this model P theta and this gate and this time evolved distribution PU. And so if you do that, then you have a heuristic algorithm to simulate quantum circuits, okay? And so we looked at some of quantum circuits. They're very simple, the simplest thing you can imagine doing, but this is what we started with, right? Like a simple quantum states that we can, if you want, proof of principle demonstrate what we're trying to do. So we took the preparation of the GHZ state and the linear graph states, and we tried to simulate them with probability. And first we tried on a 2-qubit system, so where we apply the first gate here, and then we minimize the scale divergence. And as a function of this iterative procedure we used, we see that the scale divergence goes to very small and you go exponentially fast, which was nice. And then when you apply a second gate, then you make some errors so that you still go down, at least initially exponentially, but then it saturates to a higher value. It means the higher value means that you're accumulating some error because you didn't optimize this first step perfectly. And then we took a look at multiple metrics, right? Like, so this is the KL divergence. This is the so-called classical infidelity, the distance, like this L1 distance between the probability distributions, the exact one and the approximate one. And what we see is, yes, that they go exponentially fast to 0, but there's some slow accumulation of errors, right? And this is for the GHZ state, and this is for the graph state, where we observe basically the same. And this calculation is based on a small transformer, just a proof of principle demonstration. And then, okay, so this is 2 qubits, but we wanted to go bigger because the idea is to try to scale this simulations. And we went up to 60 qubits. It's not a very easy calculation, but nevertheless, what we saw is that as we make the number of qubits bigger, you get lower and lower fidelity, but the drop is not classical fidelity, but the drop is not too high. And the other thing that we see is that if we make these models, in this case of transformer, we make it more powerful, then you get better and better fidelity, right? So that's kind of like the goal, and the message here is that we can use these probabilistic models to try to tackle this simulations in a language that is closer to machine learning, right? And so, okay, so let me switch gears a little bit, and this goes the other way around, right? Like, so in the previous part, we simulated, or we took quantum theory, we made it look like a probability theory, right? Like kind of like it, or I'd like to joke about it and saying that you take quantum theory, you make it look more like machine learning. Whereas what I'm going to talk about right now is more like you take machine learning models and you try to get them closer to quantum theory. Okay, and so we introduced this so-called recurrent neural network wave function, and this is work by my student Mohammed and our collaborators. Okay, and so what are these? So we took a recurrent neural network wave function, a recurrent neural network, and then we created a quantum state, right? Like, and so we make a coherent superposition. So in the simplest case, you can imagine that if the wave function of a system is always positive, then you simply take the square root of the probability, and then you create a coherent state, a quantum mechanical object that you use to simulate your quantum systems. But then you can also introduce a complex phase on the wave function, and we did so through basically taking the hidden state or internal state of the RNN, and then attach that phase on each of the sides of the system, so that the entire phase is just e to the sum over all these tiny phases on each side. So this is good because it allows you to encode a big bunch of knowledge that we know, like for instance, for some simple Hamiltonians, like the Heisenberg model or the transversal model, this allows you to encode, for instance, the so-called Marshall rule exactly. Okay, so it allows you to encode some of the knowledge we have about these quantum states, but it remains flexible because these neural nets are very expressive, right? And so that's basically what we did, and then we tried to compute the ground state of the transversal Ising model with 1,000 spins, and we get very, very good energies, right? Like with energy difference of the order of 10 to minus 5 with respect to DMRG, which is the gold standard in 1D. Okay, so this is this relative energy and energy variance. Then we tried the J1, J2 model again in 1D. This is a modest calculation, but we still get very accurate results especially when we start encoding this more structure, such as the Marshall sign and so on. This is the correlation functions that get out of DMRG compared with the ones that we get out of the RNN. So this is sigma z in blue, and then the sigma x in orange. And the agreement is very good. This is for 80 spins. And then we also can compute entanglement entropies and so on, and they all agree very well with our ansatz, right? Like with our RNN. And 2D, you can. So the interesting thing about these recurrent neural nets is you can define them in 2D as well. And so this is what we did. We define them in 2D, and then we try to compute the ground state of the 2D transversal Ising model above the critical point, at the critical point, and below. And what we found out is that they're the most accurate compared to, say, DMRG, which is not as great in 2D, of course, because DMRG is, if you want, gold standard for 1D, but in 2D it's much harder. And then compared to, again, a one-dimensional RNN, but also a pixel CNN, which is another paper by Carleo and Shashua, but we still get better energy. So we get really, really accurate results on par with the state-of-the-art methods. They're very accurate. And the important thing to highlight is they're very compact. They have orders of magnitude less parameters, say, than DMRG and then the other ansatz around. And then the other remark that is that unlike PEPs, which are very difficult to contract to handle numerically, these are tractable, right? Like basically you can compute the amplitude of the wave function exactly in polynomial time. Okay, so that's it for recurrent neural network.
Juan, there's a question.
Okay.
Is there a way to have exact sampling with autoregressive models in the case of continuous variables, like in the case of quantum chemistry and or lattice field theories?
Yes, there are ways to do that, right? Like to have exact sampling and on the continuum without autoregressive structure. And these models they're very popular right now. They're called flow-based models. And what you do is you first randomly sample some simple distribution, and then you evolve it with an invertible transformation. And what you get in the end is you get these two characteristics. You get samples that are exact, and you can also compute the probability P of the configuration that you just got efficiently. And yes, they're also very powerful, and they work in the continuum. They work for those systems. Okay.
I also have a question. Do you know why this 2D RNN works so much better than, I guess, pixel CNN, or why does it work?
I don't know exactly, right? Like why it works better, because this pixel CNN also encodes the two-dimensional structure of the system. Honestly, I mean,
is this at criticality? Is this at criticality?
So it's this one. So the critical point in 2D is, I think, around 3.04 or 3.06. So this this one here is at criticality. Yeah. And this the one in the middle. Yes. So, but the difference
could it be the recurrent structure makes it more, I don't know, economical to reflect long range correlation?
It could be, but I honestly, I don't have a good answer. The other thing I want to point out is that the differences are very tiny anyways, right? Like these are differences in the, I think it's 10 to the 4. So these differences are very small. So they're both really accurate. But I don't have a great answer to the question.
Very interesting. Thank you.
Okay. Yeah. So let me finalize with this. So I'm going to spend 5 minutes, if that's okay. So it's a variational neural annealing, and this is one of my newest papers, again with my student Mohammed and my collaborators. And so the idea is that we want simulated annealing and quantum annealing and simulated quantum annealing. They're very useful to tackle combinatorial optimization. And so these are because many important challenges in science can be cast at this like as an optimization problem. And this is I mean, you find everywhere, right? Like in artificial intelligence, in machine learning, auction theory, software, applied mathematics, in theoretical computer science and math. So examples of these problems are, for instance, the traveling salesman problem, nurse scheduling problem, vehicle routing that is very popular for companies such as Amazon, UPS. You can do factoring through combinatorial optimization, chip placement, which is when you have when you're designing your computer and you want to know where to place the components and so on. So there are many interesting problems that can be cast as a combinatorial optimization. And there's a connection, very deep connection established in 1983 between material science and optimization by Kirkpatrick and these authors. So they do optimization by simulated annealing. And the analogy is the following, right? Like, so you take annealing in materials and metallurgy where a crystalline solid is heated up, kept at high temperature for a while and then slowly cool down to the lowest energy configuration. And this enables control of the properties of the material. And the connection they made was, well, if you have a combinatorial optimization, you think of that as your material, and then you heat it up, but in your computer, right? Like, so what they do is they show that Metropolis algorithm, so that's what I mean by simulating the problem in your computer. Which is used, like Metropolis algorithm is used for approximately numerically simulating many body systems at finite temperatures, can be used as a tool to compute optimization, right? To solve optimization problems. And so that's the connection between StatMech, materials, and optimization, right? And so they define this idea that that simulated annealing, right? Like which mirrors this analogy or this analogous annealing process in materials, right? And the idea is you have some energy function that you want to minimize. And so you want to find this point here, this configuration S that minimizes the energy of the system or your problem, and you do so through simulated thermal fluctuations, right? Like so if you're stuck here by simulating thermal fluctuations, the thermal fluctuations will eventually possibly land you here and you solve the problem, right? Like, so this optimization or this optimization problem or this energy landscape is explored via gradual decrease in thermal fluctuations generated by a Monte Carlo algorithm, right? And then the temperature is reduced slowly such that we eventually come here, right? That's simulated annealing in 1 second, in 2 minutes. But then this inspired a lot of work, right? Like, and so there's also combinatorial optimization by quantum annealing, where instead of escaping this local minima, you do so through quantum tunneling. Okay, so what people do then is they use quantum annealing to solve this optimization problem, which is the basis of what, for instance, the D-Wave quantum computing company tries to do, right? Like they simulate some finding the ground states of some target Hamiltonian, but then they add some quantum term that drives this quantum tunneling effects so that you hope to accelerate the search of this low energy configuration. And then inspired by that idea, it's also possible to emulate quantum annealing using quantum Monte Carlo simulation. And this is the so-called simulated quantum annealing, which is based on typically on the path integral Monte Carlo and stochastic series expansion. You can use any quantum Monte Carlo technique. So these are all classical. They're very effective at solving these combinatorial problems in practice, right? And so the question we asked is, so these algorithms are very powerful, right? Like, but then we ask the question: can we simulate these techniques, simulated annealing and simulated quantum annealing, but variation, right? That's the question we asked, and then we found that this is a good idea. Okay, so what we do is we use variational principle, right? Like, so for simulating simulated annealing, what we do is we introduce a model, P theta. In our case, it's going to be a recurrent neural net, right? Like, because we want to use the fact that this models can be sampled exactly, right? And we use the variational principle to optimize the free energy, for instance, in the case of simulated annealing. That's a classical technique. And so what we do is we optimize this model so that the free energy is almost the free energy of the Boltzmann distribution. And then we decrease the temperature of the system, and hoping that eventually, when we sample the model at the end of the annealing, we solve the optimization problem, pretty much in the same spirit as simulated annealing. So we also did this for a quantum system. So we extended the idea of simulated quantum annealing, but variationally, and we do that by promoting the RNA to a quantum state, which I try to explain in the recurrent neural network wave function part. And we modify the cost function. So before we had the free energy, now we have the expectation value of the Hamiltonian on the wave function phi theta, right? And we use some driver Hamiltonian, which is the typical choice, sum over sigma x, which is the typical choice in quantum annealing. And then we quench or we remove the quantum fluctuations given by this driving term, okay? So this is, if you wanna, a cartoon. So we just warm up. For classical annealing, we have some free energy landscape at some temperature. We train the model so that we find the minimum of the energy. We change temperature, we change the landscape, and we re-optimize, and so on until the end of the annealing, when we suppress thermal fluctuations, and then we hope to be able to find the optimum, right, like of the problem. And the same is true for the quantum annealing parts, right? Like, so we start somewhere here, somewhere here we optimize, and then we change the Hamiltonian slowly. We re-optimize, optimizing the ground state energy of the Hamiltonian. And then eventually, when we suppress the quantum fluctuations, we get to the ground state of the system. So finally, so these are the results. So we found that as we make this annealing trajectory longer and longer, we see an improvement of the quality of the solutions. If you want, this is the residual energy of the solutions that are found by these models. So we took a look at variational quantum annealing, which is there are these curves here that I'm trying to signal with the mouse. And then the variational classical annealing is this one in blue and purple. What we found is that this variational classical annealing is more successful than the variational quantum annealing. And we think it's because of the fact that we're using this entropic term, right? Like in the free energy. It's this term here that promotes exploration, right? Because logarithm of P, which is the average of logarithm is the entropy, it promotes that the distribution explores all configuration states. And so I think we think that's the reason. We also look at the 2D Anderson model, which is a spin glass in two-dimensional square lattice. And we also found the same, right? Like we found that variational classical annealing, which is this blue curve, is the best compared to different versions or different flavors of variational quantum annealing, which are those two in green and magenta, I think. And then the real test came when we compared these results with traditional techniques, such as simulated annealing and simulated quantum annealing, okay? Where we found, again, that this variational version of classical annealing is superior by several orders of magnitude, especially in the long annealing regime, okay? Which means that it's a good idea to do this variationally, even though you're changing the Boltzmann distribution for an approximate distribution, but you bring the advantage that these models, these RNNs, can be sampled efficient, right? And so that's what makes the whole thing work much better. And then finally, we looked at fully connected systems, right? Like such as the Sherrington Kirkpatrick model and a so-called Wisher-planted ensemble, which is, if you want, a model that is like a bunch of configurations that are all piled up together. And then there's one that is very close in energy to all of those configuration that solves the optimization problem, okay? And the optimization has a known solution is this ferromagnetic state, but it's completely surrounded by configurations that are completely paramagnetic disorder, but that nevertheless have very close energy, okay? And so this is the specification of the model, but I won't have time to go into the details. But it's basically that. It's the hardness of like finding the needle on the haystack. And the haystack is just a big bunch of paramagnetic states close in energy to this ferromagnetic state that has the lowest energy, okay? And so what we found is we do, again, variational classical annealing and compare with simulated annealing and simulated quantum annealing. And what we found is that if you have enough time or enough annealing time, then VCA, like variational classical annealing, always beats the simulated annealing and the quantum version of it in this long annealing regime, even by a couple of orders magnitude accuracy, okay? And these are, so this is Sherrington Kirkpatrick and the Wisher planted.
So are you making like D-wave obsolete, or?
It's hard to say. It's hard to say because I mean we took problems such as like, for instance, this scale is at, so this system is at the D-wave scale. This is 40 by 40, and we've done 80 by 80, up to 80 by 80. It's just that for these curves, they're expensive because we do a lot of statistics. We sample different models and so on, but we can reach the scale of the wave. But this model has a lot of structure. It's a 2D lattice, right? Whereas these ones are fully connected, right? That they're all spins talk to all of them, and so they're much harder to embed on the D-Wave machine. But we did way smaller systems, right? Like, so we did 100 spins for the Sherrington Kirkpatrick model, but for the Wishart ensemble, so this is really hard to solve. And there's no D-Wave solution to the Wishart ensemble, but we only did 32 spins. Okay, but at 32 spins, the model is still super hard to solve. You see, like even traditionally really well-established techniques such as simulated quantum annealing and simulated annealing find it a little bit hard, right? And so it's, I mean, we're trying to make progress, but we don't know if we will make the wave.
Okay.
Absolutely.
D-Wave still has place in our life.
I think so.
All right.
All right.
Okay.
This,
so are you wrapping up now?
I'm done. Yes. Sorry, I took a little bit, a lot more. But let me conclude. So I explored a few applications of neural autoregressive models. So we explored quantum state reconstruction with RNNs and with transformers, even experimentally, which was very nice. We tried simulating quantum circuits with transformers almost without any modification to the transformer that comes from the machine learning literature. We defined these recurrent neural network functions that are very accurate, very compact in 1D and even in 2D. And then we introduced variational annealing, which is very exciting because it produces solutions that are very, very accurate for difficult problems like spin glasses. And our accuracy goes beyond the well-established techniques such as simulated annealing and simulated quantum annealing. We have a lot more. So we have, for instance, neural error mitigation for near-term quantum simulations. We have simulations of open quantum systems and more. And with that, apologize for the long time I took. And thank you so much.
Right. So there are two more questions, and maybe that's all we have time for. Another question just showed up. Annealing sometimes can have a long thermalization times in a complex energy landscape. Do you think that maybe using a parallel tempering can be used with your technique?
Yes, so this is a good idea, and we thought about it, right? Like, so, and we're thinking about doing parallel, like a variational parallel tempering technique, right? Like this is easy to do, and the hope is we're doing this annealing, and it's very interesting. But these models, when we train them, may drop modes, right? Like may not capture the Boltzmann distribution very accurately if the landscape is very rugged. But what we think is we can train these models using kind of like a parallel variational version of this idea of simulated annealing. And what we would do is we would use samples from different models at different temperatures to compute the gradients of the model, the ones that we use to train the model so that it approximates well the free energy of the system, for instance, in the classical version. And so then, yes, I think if you do that, then the gradients are going to be more accurate, and or the hope is that this will alleviate the issues that you have with the training, right? Like that you would get a more accurate free energy, but also that you would get a model or a probability distribution that samples all the modes, hopefully, of this complicated energy landscape, right? So I think this is a very good question.
Another question, have you benchmarked interacting models like Hubbard model with this method?
So we haven't done that yet, but I have an idea. I mean, this can be done, and but I haven't done it. The only thing I want to say is that these models that we looked at are interacting, right? So for instance, this the systems are interacting, right?
Now, two questions. One, is there are there quantities about the states? Is there such as entanglement, that you can use to infer whether a state can efficiently be expressed in autoregressive model. Also, can one compute the fixed points of the RNN and do something similar to ITEBD or IDMRG to work directly in the thermodynamic limit?
Yeah, so I tried this a little bit, but I haven't made enough progress to compute the fixed point. What I know is I know how to express the probability, the fixed point probability distribution of the hidden state. So this I know how to formulate, and then, but I have not. I mean, I know how to formulate, but I cannot find this expression, right? Like at least for the. But I tried. For the easing model in 1D, which is, if you want, the easiest thing you would imagine doing. And it seems like it could work, but I have not been able to work out all the details. There's some roadblocks, some integrals that I'm not able to compute. But yes, it's a good question. And then the other is there, so about the fact that can you, I thought it was entanglement and so on, that such that you know if you can express it with an RNN, or is there any quantity that allows you to know if the state would be able to be written as an RNN? So I don't know. This is also a good question, but I don't think there's an answer to it yet. Was there any other?
I think that's all the questions so far. And actually, I don't think you've taken extra time because you've been answering questions. So you've been actually, you were right on time. Perfect.
Okay, good.
All right. So I guess there aren't any more questions. So I think we can wrap up today's speaking session.